Thank you, David, very much for the invitation. Let me start with some plan for these lectures. There will be, I think, several talks and lectures about W-algebra, but since this is the first one, so maybe I just will give an overview on W-algebras. And then I will focus on specific class, which are known finite W-algebras. And I want to use some objects, which I will call Lax operators, to try to describe them. And the main, let's say, application of these Lax operators, which we can attach to a W-algebra, is that we can use them to relate these finite W-algebras, which are associative algebras, to other more studied associative algebras, which are known as. And then I think it will be useful to illustrate all this machinery with a lot of examples. So basically, the idea of this lecture series is try to find some presentation of finite W-algebras using generators relations. So this is going to be the plan. So there will be just not much representation to your W-algebra, but just let's try to see if we can find generators relations. Very easy task, at least to express, to state. So now let's start with this overview on W-algebras. And let's say in a nutshell, we could say that W-algebras are some algebraic structures which underline, are the algebraic structure underlying physical theories with symmetries. But I'm not the right person to explain this, as I don't know much about physics. But let me start from some very basic physics examples and try to see what do we get. So when I was a student in mathematics, one of the first physical theories which I met was classical mechanics. I think the course was called Physics 1, and they taught us classical mechanics. And then I studied a little bit more advanced courses on physics. Maybe it was called Physics 2. And they explained that this theory can be quantized. And this quantization leads to quantum mechanics. And there is also a procedure to come back from the original theory, which is known as classical limit. So this is something very basic which I learned. And these theories share in common that there is a finite number of degrees of freedom. Later on, I took some more advanced courses where these theories with a finite number of degrees of freedom were substituted with some theories with an infinite number of degrees of freedom. Somehow we just want to don't talk about functions, but talk about some quantum fields. The theory corresponding to classical mechanics is known as classical field theory. And the theory corresponding to quantum mechanics with a infinite number of degrees of freedom is called quantum field theory. And still, this quantum field theory is a quantization of classical field theory. And we can go back using this classical limit. And there is also a relation between, there is some way to go from a theory with an infinite number of degrees of freedom to a finite number of degrees of freedom and some attempt to go on the other way around, which I think is called chiaralization. I don't remember this procedure. I can give the excuse to the jet lag. So somehow these are, for me, the 4 basic physical theories, which I know. I know there are many others. So suppose you were a student like me, which were quite bad in physics. I was bad also in mathematics, but in physics even worse. So you don't understand very well this diagram, and you say, okay, let's try to see what is the underlying algebraic structure which describes this theory. So for example, if we look at classical mechanics, so the phase space of classical mechanics is a Poisson manifold. The phase space, it's a finite dimensional Poisson manifold since we have finitely many degrees of freedom. And what does it mean being a Poisson manifold? It means that if we take, let's say, smooth functions on this manifold, we have a Poisson algebra. They form a Poisson algebra. And this is what is known as the space of physical observable. If you don't know anything about classical mechanics, as Galileo introduced it, but if you know what is the Poisson algebra structure, you can describe the motion of a particle in the system. So without knowing anything about physics, just need to know the axioms of Poisson algebra. So what happens to quantum mechanics? So usually this phase space is, let me just say, a vector space. It's an Hilbert space in general. And what do we ask to our observable with respect to this vector space, we just ask that this act on this vector space. So our objects are not anymore functions, but are just linear operators. And what happens when we just consider linear operators? If we now apply one operator first and then another, there is no guarantee that the operation is the same if we do the inverse process. So they do not commute, unlike the case of a Poisson algebra. So these are the observables. So linear operators on V form an associative algebra. And now if we move to classical field theory or quantum field theory, this is very obscure to me, but at least the observables are objects like this. So they are so-called quantum fields. If you want to describe in some kind of naive way, they're not functions. They are generalization of functions. They are functionals. So we may think that they're just some homomorphism from certain space M, but we want that they now act on some space, some vector space V. And this M is the so-called Minkowski space-time. I have no idea what structure these elements have, but if we take particular choice, if the dimension of M is equal to 2, so these are known also as quantum fields. If dimension of M is 2, and if we just consider some particular quantum field, and these are so-called left chiral quantum fields, but I mean just consider a subspace of them, then the corresponding algebraic structure is known as a vertex algebra in the case of quantum field theory. And if we take the classical limit of this vertex algebra, we get what is known as a Poisson vertex algebra. So let's try to translate this diagram of physical theories with the corresponding algebraic structures. So to classical mechanics, the algebraic structure on the space of observable is a Poisson algebra. For quantum mechanics, it's an associative algebra. For quantum field theory, it's a vertex algebra, and the classical limit of this vertex algebra is known as a Poisson vertex algebra. So let's do this. The corresponding algebraic structure. So we have Poisson algebras and associative algebras. And associative algebra is somehow quantization. So I will explain this in a bit. And the classical limit is a Poisson algebra. So this replaces classical mechanics and quantum mechanics. And we can do the same for quantum field theory, vertex algebras. And I haven't written there Poisson vertex algebras. This is again the classical limit and the quantization. And as physicists do, we can also go back. So why there are some, let me state, okay, I will say that. So dotted arrows are not functors. That's why I'm just avoid to use a straight arrow. So because we know that there are several ways to quantize Poisson algebra. So there is not a unique way. On the other hand, these straight arrows are functors. And for example, if you have a filtered associative algebra, then we can take the associated graded. So this classical limit map is just the associated graded. And the same procedure can be done if we have a filtered vertex algebra. So, I mean, I think vertex algebra will be described very well in this event. So this gives rise to a functor between some categories. And there is also this vertical arrow, which was introduced by Zhu, I think in 95, maybe. So what is this map? So Zhu is just this Zhu functor. And roughly speaking, if we have some vertex algebra with some properties, very nice properties, we can associate to this vertex algebra an associative algebra. What do we want on this associative algebra? We want that the representation theory is the same. So that's more or less what this Zhu functor does. And the same can be done at the classical level for Poisson vertex algebras. So we have translated all these physical theories in this diagram. And previously, more or less, I just know 4 physical theories. But I think at least I know one more algebraic structure which does not appear in the diagram, which maybe is my favorite. So are you happy with all of these four, or there is something missing that you like and would like to fit? You are happy with this? It's okay. I'm not very happy because my favorite algebraic structure is Lie algebra, and it doesn't appear there. But that's the main point. So the main point that we need to remember is that Lie algebras are everywhere. And that's why they are so beautiful. So why they are everywhere? For example, I think we all know that given a Lie algebra G, we know how to construct an associative algebra. This is known as the universal enveloping algebra. So we can construct an object here. And what is the main property of this universal enveloping algebra? Well, it's the following. So if we take the commutator of two elements, this is one of the most beautiful formulas in mathematics. If we take the commutator of two elements, let's say A, B, and G, in the universal enveloping algebra, this is the same as the Lie bracket. So it seems like trivial, but we should remember that this is the Lie bracket in UG, and this is the Lie bracket in G. So this is really just a way to write the Lie bracket of the Lie algebra as AB minus BA. So this Lie algebra is telling us how far this universal enveloping algebra is from being commutative. And then there are several filtrations on this algebra. We can take the associated graded, and the outcome is the symmetric algebra over G. And the symmetric algebra over G is just the algebra of polynomial functions on G star. So G star is a Poisson manifold. Functions on this manifold form a Poisson algebra. And this is known as a Kirillov constant Poisson algebra. Kirillov constant Poisson algebra. And now there is something very similar which appears above. So if we take the Poisson bracket of two elements A and B in G, well, this Poisson bracket is just given by the commutator. So if we know this, we can know all the Poisson algebra structure of this symmetric algebra. So S of G, I'm denoting the symmetric algebra. And then there is a way to associate some vertex algebras and Poisson vertex algebra. Let me write here. So there are vertex algebras and the corresponding classical limit, which is a Poisson algebra. Let me write like V of G. So what is V of G? It's the so-called universal affine vertex algebra. And I'm not going to describe it, but let's see something similar to what happens for the universal enveloping algebra. So when we move from the finite number of degrees of freedom case to the infinite number of degrees of freedom case, namely, we should think that we are replacing G a certain infinite dimensional module. Or if you want, we just ask that on G there is an action of a linear operator. And then the Lie bracket should keep track of this linear operator. So now we just introduce a parameter, and this parameter keeps track of the action of this linear operator. Instead of having just one Lie bracket, we have some Lie bracket depending on a parameter, and this is called the lambda bracket. And okay, let's try to see if we take A, B in G, but we can take any element if you want. How far is this universal enveloping algebra from being commutative? This is a certain function, which depends on this lambda bracket, as it happens here. So this function here is just the identity for universal enveloping algebra. This is a little bit more complicated. What's the difference between these vertex algebras and associative algebras? These are not only are not commutative, also not associative. So if we try to see when this fails from being associative, this is again another function, which can be explicitly written in terms of this lambda bracket. So this is the analogy. I think it will be mentioned, and a very, very precise definition will be given. So just some non-commutative, non-associative object. And the classical limit. So VG is filtered. the classical limits of the associated gradient is this called the universal affine Poisson vertex algebra, or sometimes only affine Poisson vertex algebra. And as you imagine, we need to replace G by this module. So this is just the symmetric algebra of this infinite dimensional module. So instead of having an algebra of polynomials, now we have an algebra. Yes.
There is no C in the right-hand side. Okay.
Oh, thank you. Yeah, maybe let me write AB. Yeah, let me write like this.
Thanks for that. Just for the people at home, we're just correcting the
Thank you.
the formula so that C is included for the associator. I should have said earlier that we have microphones for people to ask questions. So if you want to ask a question, please just raise your hand and we'll get you a microphone quick smart. Thanks.
Thank you. We need to compute the now this lambda bracket over 3 elements. Thanks. And yeah, so here we just have the symmetric algebra over G, and here we have the symmetric algebra over this when we replace with this infinite analog. So anyway, this is not important for this talk, but this is just an overview. So these maps are well defined. And also these maps, I think, were already computed by Zhu in his paper. So these are also well defined. So given a Lie algebra, we have an occurrence of some structure related to this Lie algebra in any corner of this diagram. That's why Lie algebras are everywhere. But still, there are no W algebras. But you should think this as the simplest examples of W algebras. Why is that? Because now we would like to deform this diagram and construct new objects. And this new object, we are going to call them W algebras. So we deform this kind of basic diagram in order to construct W algebras. And how do we deform this? We use the so-called Hamiltonian reduction. And since I'm going to talk about finite W algebras, which are associative algebra, so let's just see how Hamiltonian reduction works in associative algebra. And I'm quite sure that Jedro will explain how this works in vertex algebras. So let's see the associative algebra procedure. And what is good about this case is that you can replace associative algebra with Poisson algebras or Poisson vertex algebra, and it still works. For vertex algebra, it doesn't work so nice. We need to work more. So the Hamiltonian reduction works as follows. So we start with an associative algebra A, and let's say there is unit. Let's say there is also a subalgebra. And let us assume that inside B, there is a two-sided ideal. So given these three objects, we want to construct another associative algebra. And let's see how could we do. So for example, we may promote I to be an ideal of A by multiplying on the left by A. But this is just a left ideal. So there is no guarantee that this will be a two-sided ideal inside A. So this is just a left module. But the action of B on this ideal AI is well defined. Maybe, namely, if we consider the adjoint action of B on this ideal, this is contained in the ideal. So the AI is stable for this adjoint action. So since there will be a problem session, this is a good exercise. And what does it mean? It means that if we take the invariance with respect to the adjoint action of B, this space is well defined, and moreover, it has an associative algebra structure. Let's denote by W of ABI. So another exercise, it is an associative algebra. And this associative algebra is called the Hamiltonian reduction of the triple ABI, or if you want, the Hamiltonian reduction of A by the pair BI. And our idea is now to perform this Hamiltonian reduction starting from UOG. So we want to deform this diagram. We want to start from UOG and start from the universal enveloping algebra and construct another object. So this is the Hamiltonian reduction of. So we have our starting object A. Let's try to find out what are B and I.
You want to pass a
So what do you mean by adjoint action here?
Yes.
Just left adjoint or?
Yeah. Thank you. So if we take an element, thank you. I forgot to mention.
And the upper script it means the what invariant space or the
Yeah.
killed by
So
adjoint action space.
yeah. So let's say if A and B are used. Okay. If you have C, D, add D.
Okay. Thank you very much.
Thanks. I was a little bit sloppy. Okay. So now we start with A, the universal enveloping algebra. And we want to define B and I. So it seems like our Hamiltonian reduction depends on two objects, but let's take one deformation parameter, let's say. And this deformation parameter is just an nilpotent element. So let's construct B and I starting from this nilpotent element. So how do we do this? So this is an nilpotent element. I never state anything about G. So let's say G is reductive. And of course is finite dimensional, of course. So if we have an nilpotent element inside the reductive Lie algebras, we can include in a triple which generate SL2. So this is known as an SL2 triple. This is guaranteed by the Jacobson-Morozov theorem. So H is a semi-simple element in SL2, and since G is reductive, it's also semi-simple in G. And then we have a grading by the eigenvalues of the eigenvalues for the adjoint action of H. And this is called Dynkin grading. So what is it? It's just the composition in eigenspaces for the adjoint action of H, where on each GK add H acts as, I'm taking alpha integers, as 2K. And now we can define some, okay, let me just use this notation. So G positive is just the sum overall eigenspaces with direct sum overall eigenspaces with positive eigenvalues. And I also will denote G greater or equal than 1 if we exclude 1/2 if it appears. Eigenvalue 1/2. Now we are ready to define B and I. So this is G positive is an nilpotent algebra in Lie algebra, so we can consider its universal enveloping algebra. We can do that. And then inside, we take the following ideal. So it's two-sided ideal generated by the following elements, all elements of the following form. So we take an element in G greater or equal than 1, and we shift a little bit by some number. And this number is the bilinear form of F with M. So I chosen G reductive. And so let me denote by this the non-degenerate invariant bilinear, non-degenerate invariant bilinear form, and also symmetric, of course. So now these are the ingredients, and they only depends on the choice of this nilpotent. Actually, I will always talk about nilpotent, but if we take two nilpotent in the same nilpotent orbits, the construction will give isomorphic associative algebra. So I should really talk about nilpotent orbit, but let me just use this word nilpotent. So let's write more explicitly what do we get.
So we have a question.
Yeah.
So is it M minus the pairing?
Yeah, the pairing with F.
Oh, okay, that's type 1.
The pairing with F. We shift a little bit, only elements which have degree 1, because of course we are taking half the eigenvalue of H, so F has degree -1 in this gradation.
So Daniela, maybe I can ask a quick question here. I have a microphone. Is there any easy way to motivate these particular constructions? So given F, why do we take the ideal to be like this?
Yeah, the fact, yeah, there is something hidden here. So let's say we have the universal enveloping algebra of G, and we act on all of G. In some sense, we would like to act only with this nilpotent group. Let's say we are looking at Lie algebra actions, but if you exponentiate this some kind of nilpotent group acting. So this is a kind of two-step process, and we can just reduce this process by performing some computation and showing that the opposite part acts trivially if we this is kind of the character of F. If we look at the inverse image of the character of F, which is exactly given by this ideal. So we are quotienting out something which comes from bigger constructions, let me say. If we look at the homological Hamiltonian reduction, we can split our complex in two parts, and one has trivial cohomology. That's the main idea. And the other one, which doesn't have trivial cohomology, we need to shift a little bit. I don't know if it makes sense. Okay, so now we arrive at this definition of finite W algebras. So the finite W algebra associated to the pair of a Lie algebra G and an nilpotent element F is the following associative algebra. So we obtain, like I've described there. So instead of ABI, let's just have our parameters G and F. So we need to quotient A, which is the universal enveloping algebra, by the left ideal in A generated by these elements. And then we need to take the invariance with respect to the adjoint action of B. And by Poincaré-Birkhoff-Witt theorem, it suffices to take the invariant with respect to the generators of this associative algebra. So we can just take the invariance with respect to the positive part of G with respect to this Dynkin grading. So this is the definition of finite W algebra. Maybe I should say quantum finite, but and the same procedure can be done in all these categories which we have written before. For associative algebras, we have described, for vertex algebras, for Poisson vertex algebra, and for Poisson algebra. So giving rise to new algebras. And the main ingredient that we use is this nilpotent element. So why the previous diagram is kind of the basic result? Because for F equals 0, very special nilpotent element, there is no Hamiltonian reduction. It's our starting point, our universal enveloping. So given such a pair, recall that we have this Poisson vertex algebra, this Poisson algebra. We also have this vertex algebra and this associative algebra. And now we can apply our Hamiltonian reduction to each corner. And this depends on F. To get new objects, so this is called quantum finite W algebras. I will just use the subscript now. Quantum comes from the fact that it corresponds to a quantum theory. A finite comes from the fact that corresponds to a theory with finite number of degrees of freedom. So similarly, here we have the classical finite W algebra. And this is something proved by Gunn and Ginsburg. Classical finite W algebra, quantum finite are quantization of this. And now if we go to this affine level, then we have.
Well, that's GF in bottom left.
So just down there, the parameters for the classical finite W.
Oh, then we have these quantum affine W algebras, which are the most important. And I think this will be described very well by Jedros. And this map, the Jew functor was computed by De Sol and Katz in, I guess, 05. And then we have the classical limit, which is this classical affine W algebra. And the map, which is similar to the construction similar to the one which was done by Gunn and Ginsburg, appear in a work with the De Sol and Katz and myself. And later we also compute this map, Jew algebra in the classical case. So just to say a few words, so this classical finite W algebra is a Poisson algebra on which manifold? So it's the algebra of functions on the Zlotovy slice. So it's a certain affine subspace inside G star, and was used by Zlotovy for studying singularities of coadjoint orbits. So all these algebras were introduced with different ideas in mind. These quantum finite W algebras were originally studied by Constant, a principal nilpotent, and I will explain later why. Or maybe I can spoil and say now. Constant proved that this, for principal nilpotent, this algebra is isomorphic to the center of the universal enveloping algebra. And more general definition, similar to which I said, came later by Bremet. I think in 2002, and constant was something maybe 78, not sure. And these quantum affine are the most important and most beautiful object in this picture. They originate from conformal field theory, but have so many applications in mathematics that the margin is too small to write. And a lot of people here work on this and got very nice results. The classical limit, this classical affine, are kind of generalization of some work by Drinfeld-Sokolov in integrable systems. So they are related to integrable system and the so-called Drinfeld-Sokolov hierarchy. So they all have very different applications when they were introduced, but it's nice that somehow they're all related in a unifying picture.
Sorry, what is the word we done on the after
Hierarchies of PDEs. And the margin is becoming smaller and smaller. Yeah, it's nice that these Lie algebras are also related to hierarchies of partial differential equations. Okay, so we won't focus on the most interesting part, which is Jethro's job, but let's try to see if we can say something for this quantum finite W algebras, if we can write some presentation, as I tried to state at the beginning. Are there other questions on this overview? I just wanted to give an idea of what these objects are. So now if there are no questions, let's do something very basic. Let's pick two nilpotent elements which are very famous. And let's see how can we describe this quantum finite W algebra. So it's kind of, let's do some exercise. Oh, I got confused. Okay, so let's see some basic examples. So the first basic example is f equals 0. So we have already mentioned this. We are not doing any reduction. So this W algebra is the universal enveloping algebra. And let's try to see if we can find the generators and relations. So generators in the sense of the PBW theorem. So what is a system of generators, or sometimes what is known as what is a PBW basis? So a PBW basis is just an ordered basis of the Lie algebra G. So this is just an ordered basis. And can we write down the relations? And we already have done in general. So the relations will be just ui uj equal ui uj, but this, I just remind you that it's just, you should understand as ui uj minus uj ui. It is in the universal enveloping algebra. So let's see what happens in another case. So the so-called principal nilpotent element. So this principal nilpotent is just the sum of the negative Chevalier generators. So there are as many as the rank of G. And just to have some ideas in mind. So if we take SLN, this is just one nilpotent metric, is a nilpotent metric with one Jordan block, a nilpotent Jordan block. Okay. So what can we say about this? Well, there is this Kashdan constant theorem, which says the following. So WGF, let's say F principal, is isomorphic to the center of the universal enveloping algebra. So in these two cases, these W algebras are very explicit. In particular, this is a commutative algebra in this case. And how can we describe this in terms of generators and relations? I just remind you that this is now a certain polynomial algebra in variables U1, let me call this R, U1, UR. So if we say that there is if we call this isomorphism, let's say rho, we can describe explicitly this W algebra as follows. It's just a polynomial algebra in generators W1, WR, where each WI is just the image of a generator of the center of the universal enveloping algebra. We can just use this isomorphism by Kashdan constant. And relations are very easy now. This commute, so WI, the commutator of WI, WJ is 0. So in these two cases, it's very easy to describe these algebras. and it's very explicit. Let's try to be even more explicit. So let's choose now G to be GLN. And let's see if we can say something more.
How hard is the question close up theorem? Is this a hard theorem to?
Yeah, we will see in for GLN. I will give you some ideas. Yeah, thanks. Yeah, what I want to focus for GLN, but it works for any algebra, what I'm going to say. Okay, so let's fix now for simplicity GLN. So let's maybe say sub-example now. And now let's see what happens for f equals 0. So W is universal enveloping algebra. Now let's fix an explicit basis. So the basis given by elementary matrices. And I will denote by EIJ. And you can choose any order you like. Let's rewrite the relations. This is one of the first formula that we learn in Lie algebra theory. We can write this very, very explicit. But let's say, okay, we don't like indices very much. So let's see if we can get rid of the indices. What do we need to do to get rid of the indices is just to collect all our generators into a generating series. And for us will be just a generating polynomial. So let's collect all the generators. So we define this capital A, which is Z times the identity, plus a certain matrix E. Now with V, I'm just denoting an n-dimensional vector space. And I want this object being a polynomial with coefficient in the universal enveloping algebra, but also we want to tensor with the endomorphism of V. So this is just a matrix whose coefficients are polynomials in the universal enveloping algebra, and I'm using this variable Z for the polynomial part. So I need to define E. E is the collection of all our generators. E is a matrix, and I want to collect in this way. In position ij, there is the generator ejI. So this is the following element. So this is a matrix which coefficient in the universal enveloping algebra. So if you think at B as the standard representation of GLN, this is the Casimir of the representation. Okay. So now if we take this AZ and try to rewrite the formula for the commutators, and if we try to rewrite this, what do we get? Then this formula is equivalent to the following. So now we want to express the commutator in terms of our generating series. So on the left-hand side, there should be the commutator of AZ and AW. And this is equivalent to the following object. And I want to have everything polynomial, so I will just multiply by Z minus W here. So I need to explain what is omega. So omega, it's a map from B tensor B to B tensor B, which is defined as follows. So the monomial V1 tensor V2 is mapped to V2 tensor V1. So this is just a different way to rewrite all these relations. And we don't have indices, so it's a little bit better, but we have operators, so it depends on what you like. But what is important is that this is the defining relation for an associative algebra, which is known the Yangian of GLN. So this is denoted usually by WGLN. So why it's useful to show that the relations can be equivalently rewritten as follows, because now we have a map from the Yangian to the W algebra. So we found an object here, which obeys all the defining relations here. So we just got a map. And this map is very studied in theory, in classical theory of the Yangian. It's called the evaluation map, and is surjective also. So it's nothing new. It's just a different way to rewrite the relations for the universal enveloping algebra. So this map is called the evaluation map. It is surjective, and as a consequence, our W algebra can also be taught as the quotient of the Yangian by the kernel of this map. What is the advantage of doing something like that is that the representation theory of the Yangian is very well known, for example, so one can pull back to the W algebras, but at this level is already everything well known because we are talking about, never forget that this is just a universal enveloping algebra, so nothing new.
This evaluation map, is it you take z equal to 0 or 1 or something like that to go from the y to w, or?
yeah, let me write it. So let's say there is a certain generating series here, and we map this generating series to A of Z. So we will explain later in the next lectures more precisely. But the idea is that there is some generating series which satisfy this relation with T in place of A. And then the map just sends T to A. That's why it's called. Think of this being infinite series, really infinite, not a polynomial. That's why it's evaluation. We are evaluating some coefficient at some special point. Okay, now let's do the same for principal nilpotent, where just we have this. Okay, now let's continue with the same idea for principal nilpotent. So our algebra now is polynomial algebra. And the rank of GLN is n. So we have n generators. They commute. So Wi, Wj is 0. But let's do the same process as before. Let's get rid of the indices. Let's try to see what happens. So we need to collect all the generators in a generating series. It will be again generating polynomial. Let me call this L. So now what is this? This is just a polynomial with coefficient in the W algebra as before. But let me be a little bit stupid. Let me tensor this with NV, where V is now just C. So let's try to be very close to what we have done before. So now it seems like, okay, if we take this relation and we plug, we multiply by some power of Z and we take the sum, what do we get is the following. So nothing very inspiring. But let's rewrite this in a kind of more complicated form. So this relation becomes the following. You may check that these are equivalent. So the commutator of LZ LW0 is equivalent to the fact that if you multiply this commutator by Z minus W, it is equal to LW LZ minus LZ LW. So these are equivalent. And now let me be pedantic as before. So omega of V is just one tensor one, if V is just a one-dimensional space. And of course, C tensor C is isomorphic to C, so there is no harm to put a tensor product here. There is no harm to put a tensor product here. And this is exactly the same formula as before. Now, not for GLN, but for GL1. This is defining relation for the Yangian of GL1. And similarly to what we have done here, so we have a certain map from the Yangian of GL1 to the W algebra for principal nilpotent. And again, we can show that this map is surjective. Let me just denote this map by K. And as a byproduct, this W algebra is isomorphic to this Yangian of GL1 modulo the kernel of K. So both this A and L satisfy this kind of, let's say, Yangian identity. So the question which comes after is there a relation between A and L? So if we can find an answer, then maybe we can try to generalize to arbitrary nilpotent. We start with some A, we apply some procedure, and we produce a generating series for the W algebra. And we try to see if the relations are the same of our starting point. Maybe for a different representation. We move from the standard representation to the trivial. But who knows? So we need to answer this. And for doing this, we need to understand a little bit this rho. So let me just remind you that Wi are just rho of Ui. Maybe it's still written. No, it's erased. Where rho is this isomorphism. Let me write in this. Rho is this isomorphism. So this is denoted by the generators here, we denote by U1, UN. So the question is, can we find the UI are element of the universal enveloping algebra? Can we find some expression of these elements? Because if we can find some expression, then in some sense, this L is obtained by applying rho to our matrix A. And in order to do this, we need to remember linear algebra. So first of all, the center of GLN is a quantization of the algebra of invariants of the symmetric algebra of GLN. And how do we find this invariant? We compute the characteristic polynomial of a matrix. So let's do it. Let's go back to when we were students.
So Daniela, you mean quantization here in the sense of your diagrams from the start, right?
Yeah,
Because
exactly.
normally a quantization would be non-commutative. And this
Yeah,
one is
exactly. Yeah, as a
it's a trivial quantization.
yeah, exactly. So let's do it. Maybe let's just fix n equal to for the moment. So n equal to, even simpler. So we take the following matrix, which you may think is a classical analog of our matrix A of Z for the universal enveloping algebra. So now this is an element here. And we compute the determinant. So this is telling us that the algebra of invariance is just the algebra of polynomial in these two entries, two variables, trace and the determinant. Or this we know very well, right? And now let's try to understand what does it mean that the center of GLN is a quantization. So let's just do n equal to since it's late. So how to find generators in a similar fashion by taking the characteristic polynomial for the center of the universal enveloping algebra of GR2? Well, we do exactly the same. So we compute the determinant of this. But now these are elements which are non-commutative, they lie in the universal enveloping algebra. So the determinant is not well defined. For this reason, we all agree that we just use Laplace expansion corresponding to the first row. So if you always do that, the result will be well defined. Let's agree on this. So this row determinant means Laplace expansion with respect to the first row. So there is no ambiguity if you do this. And let's also make some shift. So let's see what happens here. We get some polynomial. And you see, if we take the filtration given by the degree, when we take the classical limit, this constant disappears. So here we, a plus d minus 1, the highest order term is a plus d, which becomes the trace. And here, the higher order term with respect to the filtration given by the degree is the determinant. So in this sense, it's a quantization of the universal enveloping algebra is a quantization of the algebra of invariance. And this is what we have denoted by U, I think, right? Ah, yes. So these are our U1, U2. Now, if we can apply ρ to U1 and U2, we found our generators, which means that we can apply ρ to this matrix. And now we need to explain a little bit about this map ρ. Is it clear in which sense is the quantization? Yeah, then unfortunately the Poisson bracket becomes trivial when you do this procedure in this case. But it happens also for the universal enveloping algebra. If you take different filtration, you can get a trivial algebra or you can get Kirillov constant Poisson algebra. Depends on what you choose. Okay, so about ρ. So ρ is the following map. It's the map from U of GLN to this ideal. I'm not going to write. So these are the generators of I. So what happens that this map, this is just a left module. So this is not an associative algebra map, but what Kazhdan constant proved that if we restrict to the center, then the image is the W algebra. Okay, I'm using G because it holds for any G. And moreover, it is an isomorphism. That's more or less the idea to prove this theorem. So we take this map, which is not an associative algebra map, but we restrict to the center. Okay, so for us, then what's going to be L of Z? Well, we need to apply ρ to this ρ determinant because we have defined just these W's of written. So Wi is just ρ of Ui. So if you apply ρ of Ui, it's the same as apply ρ to this ρ determinant of the matrix. This is the matrix which we have denoted A of Z. But we need to pay attention because there is some shift. This is some quantum effect, which does not appear at the classical level when we study linear algebra. So this is the so-called shift matrix. And what is very nice about this is that, moreover, we can bring ρ inside, even if it's not a map of algebras, we can put inside the ρ determinant. So this is something very peculiar which happens. So this is also an exercise that you can prove. But these two simple examples suggest a strategy, which is the following, and then I'm done. So the strategy is that we start with A, we apply our map ρ to a certain object, and we end up with an operator with values in the W algebras. And seems like the relations are the same, but just for a different representation. So these A and L, we are going to call Lax operators. in a sense, we are just trying to rewrite the Hamiltonian reduction in terms of generating series. It's an enveloping algebra. It was our starting point. And the generating series is this kind of Casimir that we have introduced. Then we apply our map, the map which was used by Kashdan constant, this rho, and a little bit too big. Okay, this means that we are now just apply rho to A. And then we want to compute the invariance. Okay, we want to compute invariance inside this space. And to compute invariance is very similar to what we did in linear algebra. We need to compute a determinant. So now when we move to W, we do some procedure to this rho of A. And in this particular case, the procedure was to compute this rho determinant. If we want to generalize to any nilpotent element, this rho determinant is not sufficient. So this will be something which is called quasi-determinant. And what appears here that it doesn't appear at the classical level when we compute invariance of matrices is just that there is a shift matrix, which I'm going to denote by D. So this is the way we want to construct some operators. And then the question is, what are the defining relations satisfied by this? And I hope I'm going to address this question. Okay, that's it.
All right, do we have any questions? Well, I'd like to ask a question. So this shifting seems a little mysterious. Is it related to the fact that you have the character in the definition of the W algebra? Or is it a completely different phenomenon?
Yeah, it's the following phenomenon. So when we want to quotient, it's related to the character, because when we want to quotient, we need to bring everything which has the character on the right, and then we can quotient. This is the meaning of this not being an associative algebra map. And when we bring everything to the right, we need to commute using the relation of the universal enveloping algebra. So when we commute, some numbers will appear. I hope to give an example on how this works. But what is very nice is that we can write this matrix explicitly.
Okay. And so this is maybe the same question in disguise, but in geometric quantization, there's something called the metaplectic correction. And when you do this in Lie algebraic settings, you always end up with, weights getting shifted by the Weyl vector, the level gets shifted by the Dewey-Coxeter number. Is this also the same type of?
Yeah, no idea. Okay. It would be nice to check, investigate, yeah.
Any more questions, please? Yes, Tomiyuki, do you have a microphone?
The types, they don't have evaluation map, right?
Yeah, exactly.
What do you do?
Yeah, we use that's why I wanted to stick to GLN. For symplectic and orthogonal, we need to use a twisted Yangian evaluation. Yeah, sorry, when I say it holds for any G only from the part of universal enveloping algebra. For Yangians, we need to use some other algebras.
Any last questions?
Can you hear me?
Okay, grab the microphone, please.
The subscript R is in this case 1 omega R. Subscript R attached to omega is in this case 1.
Yeah, 1 is 1 tensor. Yeah, you are right. It's yeah, they're all the same, right? Okay. Yeah, I mean, everything was trivial just to emphasize that the structure was similar to the.
No, I mean R. What's R?
R?
B. It's B. Oh, I'm sorry.
B is C.
Omega B. Okay. I see. I'm really confusing.
Any last questions? Do you want to pass the?
I guess I was a bit confused about the formula there with the bracket of L's. So maybe the one with A's. So A was a series in GLN or U of GLN tensor endomorphisms of.
Yeah, and this is similar. U is our W algebra for f equals 0.
Yeah.
This should be something analog.
And then, so the tensor product is in that algebra tensor itself. And then omega is in V tensor V.
Yeah.
So
because I haven't written, okay, it doesn't mind where I write. I haven't defined very explicitly, sorry about this. So we want to take the generating series of all the coefficients. So eventually this will be just tensor some matrices. Since I'm very lazy, as you have already checked by yourself, so I can get rid of this And so this is an identity in this space. And if I wanted to be very, very precise, I should have said this is one in the universal enveloping algebra tensor omega. Thank
okay.
you.
So it's just swapping the
Yeah,
B factors
thanks.
and identity. Okay.
Yeah, I always tend to remove the tensor product on coefficients. Sorry about this. It's,
Okay.
I know it's confusing sometimes. Sorry. For me, it's easier, but I understand.
No more questions. And let's thank Daniela again.